In terms of the EDA tools that we provide and support, this includes all these are mentor graphics tools. This includes the layout, PCB layout, as well as schematic capture. And we also have the enterprise level for PCB layout with Expedition. In addition to that, we have signal and power integrity solutions using hyperlinks. Today's discussion is going to center around the ModelSim and Questa product, which is used for FPGA, ASIC, and system simulations. We also have products for thermal analysis, as well as design for manufacturing and assembly with Valor. And at this point, I'd like to turn over to Walter. Walter?
Yep. All right, can you hear me okay?
Sounds good.
All right, so what we're going to talk about today actually is a little bit, it's not so much the ModelSim and Questa simulation tools, but our Questa Formal tools and a couple of specialized solutions based on that. And so, you know, really it's all about, you know, how you go about verifying and when you verify your device. Traditionally, you know, it was a lot of manual code reviews to make sure the code looked okay, some amount of simulation, and then getting it into the lab to do prototyping as quickly as possible. You know, when we're looking at today's Zinc or Stratix 10 that have an ARM core and, you know, hundreds of thousands, if not millions of gates of logic, lots and lots of clock domains, very fast clock speeds. Some of these traditional methods are starting to break down, especially when you get into the clock domain crossing type issues. You know, like I said, we have more than a million gates of design. We're starting to see that even FPGA designers are starting to have ASIC-like challenges. The thought always was, hey, if we can get this into the lab as quickly as possible, we can run at speed and we can find things, you know, much more quickly. Well, two things are happening now. One, debugging in the lab is very difficult because you have very limited visibility inside the device. And also when you find an error, to go through the synthesis and place and route and burning a new chip, that spin can take 6-8 hours itself. So just to make a quick correction and then re-get it into the lab can be an 8-hour process. So we're starting to see a lot more FPGAs adopting RTL and formal verification methods, ASIC-like verification methods. And it's all about finding the bugs early and maximizing your time there. Kong, I don't know if you can mute other lines. So one of the things we see is, you know, people say, hey, if we just had a faster simulator, we could get things done much more quickly. And the problem there is when you're looking at really big designs, the simulator to completely verify a device will take, you know, this simple 2-bit or 32-bit comparator. It's comparing two 32-bit vectors. And if they are equal, then the E line is 1. Otherwise, it's a 0. To simulate that in a simulator, that's going to be 2 to the 64th vectors. So even with a super fast simulator, that's going to take forever to do. But if you look at formal verification tools, and that's what we're going to focus on today, formal verification takes this problem and they kind of turn it around and look at it from a different angle. And it's not, given the stimulus we put on this circuit, did it cause an error? It is, given this circuit and given this assertion that I've made about this circuit. And that is, I assert whenever A equals B, that E will be a 1. So I've made this assertion, and what formal verification tools do is they try to calculate a set of stimulus using formal state space analysis tools that will violate that property. And they will either come back with a proof saying it is impossible to violate that, or they'll come back with a counterexample that says, if you put this on A and this on B, you will see an error. And formal verification tools, especially with this circuit, since there's no flip-flops, no memory involved, that's instantaneous. And so you can get these formal proofs much quicker for certain types of circuitry. And so that's kind of the difference. Is formal is saying, can I calculate a set of stimulus? Can I look at the equations involved here and come up with a counterexample? So simulation, as I said, is once you start to add memory elements to things, what simulation does is it applies some stimulus and it causes this circuit to kind of move through its possible state spaces. And what you hope is that you hit some errors that are going to cause disruptions around these stars, which are these properties, these assertions I've made about that circuit. So it's very dependent on the stimulus you give it. If you don't give it the right stimulus, it won't uncover an error. What formal is doing is it's saying, given some initial state, let's calculate every possible state this circuit can go into and see if it could possibly violate that assertion. And so it's all about, that initial state is probably reset, but it could be based on some simulation. You could run some simulation vectors and say, okay, calculate formal from here. So that's really what the difference there is between formal and simulation. And it's all about, calculating every possible place you can get to. So formal used to be very difficult to run because you had to have these experts who could write those formal properties for you. And so it was kind of an expert level tool that required a formal expert to run it. So what we've done recently is we've started to take that formal engine and package some applications around it where we've done the work for you. And so today's, what we see is instead of being that expert level tool where you have to have these experts writing these things, we've got these fully automated apps that are just push button ready to use pretty much. So the two that we're going to talk about today are Questa Autocheck, which is basically sort of a linter on steroids, I'd say. It is a set of rules, but it's got that formal engine to back up the analysis that it does. And it's basically you take your RTL circuit and you compile it in the same way you would compile for simulation with ModelSim or Questa, and then you push the auto check button and it performs about 40 or 50 different checks on that design that are all built into AutoCheck. From AutoCheck, once you have that, you can get into some of our other apps. Cover check is all about, when I've got a coverage report and I don't have 100% coverage, are those lines that are not covered, are they reachable? Are those conditions reachable? And so that formal engine does that. X check is about figuring out whether propagating X's could be a problem in your design. Secure check is all about if I have a design that has any kind of encryption or security involved. And so if there's any data that should be protected, what secure check does is you say, this data right here, there should only be one possible path, and this is it for read and writing that. And then maybe there's two paths for reading that, but they shouldn't be able to write it. So you identify those paths, and then secure check goes through and it figures out whether there are any backdoor paths to either read or write those secure, maybe encryption keys or whatever, just whatever that secure data is. And then if you come over here, property check, that is that expert level tool where you're creating your own properties. So those are all kind of Autocheck is the entry here, and then you can add on these other things. The other kind of tool that's built around our formal engine is our clock domain crossing tool. And so that's all about saying, okay, here's the clocks in my design. These are synchronous to each other. These are asynchronous. Now do a clock domain analysis on this using that formal engine as a backup. So it's kind of a much better tool. I know Xilinx and Altera do have some CDC analysis things just in the tools, but they're going to give you a lot of false positives and then, false negatives. So it's going to say that there's errors that are maybe not really errors, and it's probably going to miss some things that are actual error, CDC errors that you won't find. And so that's kind of what the CDC tool is all about. And so we'll talk about Autocheck and CDC in more depth. So if you want to get more information after this presentation, I highly suggest you go to verificationacademy.com. This is a Mentor Graphics sponsored education website. It's free, and there's a whole bunch of information, not only on these formal-based tools, but on just verification methodologies in general. So I highly suggest going and taking a look at Verification Academy. So let's see. The Questa and CDC tools, like I said, what we've really tried to do is package them to be more user-friendly so that you don't need to be an expert and you'll start getting good results as soon as you use them. So first, let's talk about Autocheck. So what Autocheck is all about is running your RTL code through this tool before you have a test bench, before you have anything else. You can do it at the block level, you can do it at the subsystem level, and just try to identify as many bugs and fix them before you do any simulation, just to try to get the highest quality code as soon as possible. If we look at where people spend their time in trying to test their design, they spend about a quarter of their time planning the testing. They spend a quarter or 15% of the time planning, about a quarter of the time writing the test bench. 22 or like about another quarter of the time is spent running those tests and just waiting for the machine to finish them. And about 40% of the time is actually spent doing debug. So Autocheck is meant to eliminate the planning and the development and everything else. It significantly cuts down this running and trying to find these bugs, and it really helps with the debug. So first we'll talk about Autocheck. What is it? How does it work? And it's really about taking your RTL code and running it through and applying a whole bunch of different tests, whether it's combination of loops, error math overflow, all kinds of different things. And it's just that simple. You compile your code and hit Autocheck. And then what it does is it comes up with a set of definite errors and cautions, and then has a whole debug flow built around that, where it'll say, hey, I think I see a combinational loop. You click on that error, it'll show you a schematic. If it's a timing-based issue, it'll generate a waveform database for you to look at. If it's things like deadlock code, it'll show you the state machine and why things are deadlocked. So the flow, as I said, is take your RTL code, compile it. You may need to create some constraints like, what are my clocks? What are my resets? If there's any tied off pins or anything like that, and you hit go and you get this result. So it's all push button, gets you as early as possible to start to find errors before you've even developed the test bench. And it really just improves the quality of the code that's coming into your verification effort. So it's more than just a static linter, as I said, because it's using this formal engine to do a state space analysis. It's very fast compared to simulation, and then it's really good for reporting and debugging those issues. So really what it does is it takes your RTL code, and when you compile it, it kind of comes up with a generic synthesis that it does, and has a formal net list that then it does all these type of checks. So I kind of mentioned some of them. There's some X stuff. There's uninitialized registers, unreachable logic, and state machine checks. The things that are nice is like arithmetic checks. So it'll let you know if it's possible to override the 32-bit bus that you've set up, or to do divide by zeros. It'll do bus connectivity checks, things like that. The errors then come up in this design check down here. When they first come up, they'll all be uninspected, and then you can go through and you can kind of say, oh yeah, that's a bug. Here's, I need to fix that. This one I believe is fixed, so it's going to check that happens the next time you run Autocheck. Maybe there's things that you're going to waive, that you're going to say, that's an error, but I'm going to waive that because I can't touch that code, maybe because it comes from a third party, and I've done some analysis that I've decided that's not going to be a problem. So as I said, Autocheck is kind of like a linter, but it does more. It is somewhat complementary. Lint tools a lot of times will do, we're going to do syntax checks and semantics. I don't know why they don't list that here, but style definition, naming conventions, that you need an _L on all your active low signals, things like that. Those, some lint tools can do that. But other than that, what Autocheck is doing is not only is it doing rule-based checks that are static, it's adding a temporal aspect, the timing aspect to that. So they're assertion-based, and that's what I think that means. Assertion-based versus rule-based is that there can be a timing aspect, a protocol aspect that we add. And then we're using these formal engines to back up the analysis. So they are complementary. So here's an example of something that a lint tool would say was fine, but because of the formal engine, we would catch it. And that is, a lint tool would look at this and it would say, everything's good here. If I look at my state machine here, to get out of pass, to get out of this continue, if enable is 1, you go to idle. Otherwise, if enable is 1, go to pass. Okay, that's something that probably a static tool would find, and that even looks, that should have been if enable is 0, then I go to the state passed. I think that should have been a 0. But what I do notice is, so yeah, I think that was the intention here. Typo that I hadn't seen before. So a static checking tool would say this was fine. But what you notice is if you look at the logic for enable up here, enable is saying not A and in B and start. So all 3 of those have to be a 0, or this one has to be a 0, this one has to be a 1, and this one has to be a 1 in order for enable to be true. But if we look at the logic for start, the only time start is true is if A and B are true. And so what'll happen is enable is actually stuck at 0. A static checking tool, like a linting tool, will not find that, and it would say this code is okay. Whereas with our tool, we are looking at that logic and we'll find out that that enable is always a 0. And so another way is even less obvious. Here, you could probably figure that out. Here, what we've got is a similar situation where we've got this signal coming in from another block of code. And again, a static tool is going to say this is all okay, but due to the state space analysis that our tool does, it'll find that when we're in this state, this signal is always a 1 or always a 0. And so it'll lead to things like deadlocked or whatever states. So if you look at the approach here, what's happening then is that we create this formal model. We're running it through a bunch of different formal engines and doing that state space analysis. So other types of checks that we're going to find is things like arithmetic checks. We'll be able to detect if you're going to get a divide by 0 or if your buses are going to overflow. If you have tri-state buses, we'll figure out if there could be multiple drivers, and we'll find conditions that if you do this, you'll be driving that signal from 2 different places or not driving it at all. And then the debugging and things like live lock and deadlock. I think this will be more interesting when I show it to you in a demo. So combinational feedback loops are the other type of issues that our Autocheck tool will find. Multiply driven, clocks as data, all kinds of case statement checks. So all of this, like I say, is built into Autocheck. You give it your RTL, and it will start to find these errors. And this is just a soft machines started using Autocheck, and they definitely said that they're finding that their code before they bring it into their verification environment is, they're just finding a lot of bugs that would have taken them a long time to find in their verification environment with Autocheck before they ever get there. So it's really all about finding bugs as soon as possible. It's automated. It's just push button from a user point of view, good debug, and an exhaustive state space analysis. So that's kind of the Autocheck overview. Next, I'll kind of go into CDC. So CDC is our clock domain crossing solution. If we look at ASICs that are being done these days, we see that on average, there's probably about 7 or 8 clock domains. The most probably have 4 or 5. We get up to like 50 or more, and very few only have a single 1 or 2 clock domains. So that's from the ASIC world. And then we also see that clocking is probably the second most common error. So it's functional verification or functional bugs. So things that are wrong in the code is the most common, but then clocking is the second most common problem. One of the things that I finally have pushed these surveys that we do is to look at not only the ASIC world, but also the FPGA world. So if we look at FPGAs, we'll see that they're actually pretty similar. There's probably not as many up here on the high end, on the 50 or more clock domains, but we are still seeing that the most common is 3 or 4, and if you average this, it's probably 7 or 8, and there's a lot that are in this 10 or more clock domain area. So clock domains, and then if we look at at the errors, we'll see functional bugs, most common, and we actually see more clocking issues in the FPGA world than if you go back to that ASIC one. So just as important in the FPGA world is clocking issues. And often it is those asynchronous clock domain issues. And if you know anything about asynchronous clock domain issues, those are notoriously hard to find, because if you run the same data through the chip again, that asynchronous issue probably won't show up, because it only shows up once in a while. And so what are we talking about when we're talking about these asynchronous events? And what we're talking about is basically setup and hold violations. So if the clock is coming along and the data changes too close to the clock, what we'll see is the output will kind of go metastable for a while and ring, and then it'll either go to 1 or it'll go to 0, and it's unpredictable what it will do. And it might even ring for, forever. So 1 in 4 ASIC respins are caused by CDC issues. If you look in the FPGA world, there's probably a whole lot of asynchronous issues, and it's, if you're using your modem or your wireless at home and it flakes out on you, good chance that that's probably some sort of an asynchronous issue. When you have these issues that just kind of show up once in a while and you don't know what's going on, it's a good chance that that's due to asynchronous problems. And if we look at today's designs, you've usually got a subsystem, something like this, where you're bringing in data over USB, over Ethernet, maybe over PCIe. You've got UARTs and GPIO, and all of these are going to be different clock domains, and they have to be synchronized in to the main chip domain at some point. So this is all places where these many clock domains can cause these asynchronous issues. And it really comes down to whenever a signal crosses from one domain to another, you have the potential that this register could go metastable. If these are asynchronous to each other, you will have a setup and hold violation at some point. It is unavoidable. We kind of talked about this, what it is, and it's basically if the data is changing too close to the clock edge, you can get a setup or a hold violation, which will cause metastability, and then it'll cause it to go to some unpredictable state, either 0 or 1. Simplest way to fix that on just a single bit is to add a 2 flip-flop synchronizer. So if we look at this, as I said, this will have some metastable event at some point. Let's say based on the clock frequencies and whatever here, let's say once an hour, this thing goes metastable. If I just put a second flip-flop right here, the chances of this signal going metastable goes from once an hour to once every 100,000 years. So you virtually eliminate metastability just by putting 2 flip-flops. So for a single bit, a 2 flip-flop synchronizer is all you need. And basically what you do is you take away that metastability on this line, and what you do instead is it's either going to take 1 clock cycle or 2 clock cycles to get through this synchronizer. So you trade off this metastable event for an unknown delay through this synchronizer. It's really what happens there. But if you think about it, even this simple 2D flip-flop, there's a protocol that I have to follow here. So let's say this clock A is running at 100 megahertz, and this guy is running at 50 megahertz. That means that I could, if I only put a 1 pulse wide, a 1 clock wide change on data right here, data could go high and then go low again before this second clock domain ever captures it. So basically what that means is the data rate on TX data has to be less than or equal to the clock rate right here, so that I guarantee that I'll catch any changes on that data. So even this simple thing, I have some timing issues that I have to meet. If I have things like buses, now I can't just put 16 2D flip-flops, synchronizers on a bus, because what'll happen is each one of those will have a different delay, and so there'll be 1 or 2 clock cycles where this bus will be total garbage. And so in the case of a bus, I have to have a more complicated synchronizer. What I have to do is maybe hold the data, pass a sample signal over, say go ahead and capture the data, and then take that sample signal away, and I have to make sure that I hold that data constant for the entire time it takes that protocol to happen. So not only do I have, is there a proper synchronizer here? So that's the first thing. Do I have a synchronizer? And is it of the proper type? The second thing is, have I implemented the timing protocol correctly? So can I violate the timing required by this thing? Now let's say that I've done the analysis and I say, hey, there's a proper synchronizer here, and yes, I cannot violate that thing. So right here, this one's good. And then I do the same analysis up here and say, yep, this synchronizer is also good. So I've got 2 different paths here. I've proven that both of those paths are okay. But let's look at this. On the same clock cycle, I change these 2 signals. So they're in sync with each other right here. And then somewhere down the line, and this could be through some sequential logic, so there could be flip-flops along here, but somewhere down the line, these 2 signals come back together through a logic cone and get sampled. And the question is, these were in sync right here. And now, because of the nature of a synchronizer with its unpredictable delay, these 2 signals, they could be out of sync by plus or minus 1 cycle with each other. And so that's called reconvergence. Do I have an issue when I have signals that were synchronized to each other in one domain, and now they're out of sync after I've crossed them over? And so what our tool does is it does all of that analysis, the structural analysis, the protocol analysis, and then finally the metastability injection. And what that means is we detect every place that there would be possibility for asynchronous, for metastability events to occur. And then we track all and calculate all the reconvergence paths, and then make sure that when you run your test bench, that it's, this one was fast, this one was slow, they were both slow, they were both fast, this one was fast, this one was slow. And we use your test bench to make sure that you've done enough analysis that it's still passing even though all these things have happened. Where are we on time? Okay, we got plenty of time. So that's our CDC solution. So if you buy Questa CDC, you get our CDC solution. You get one of those CDC effects engines. You get the structural and protocol analysis. This is really for gate level or for ASIC stuff, so don't worry about that. These 2 are both directed at ASICs. So you get this. There is an add-on called Reset Check, which does a very similar analysis on your reset lines and making sure that when you're coming out of reset, you don't have asynchronous events that can cause problems as well. So one of the things we're really proud of is that the ISO 26262 is a new automotive standard that's out that basically is anything that's going to go into an automotive system needs to meet the ISO 26262 standard. So all of the simulators on the market, Questa, Cadence, Incisive, and Synopsys VCS, they have all been certified by ISO 262. So that's good. We are the only CDC solution that has currently been certified by ISO 262. All the other solutions out there, ISO 262 says they are not complete enough. So if you want to get an ISO 262 certification, you have to use Questa CDC to do it. So what's driving the adoption is, like I say, the designs are getting more and more complicated. There's more and more clock domains. And, you know, this is very high performance. It's scalable. It's accurate. And then if there are problems, it gives you the guidance on how to detect those. Yes.
There was a question from Gary. Did you answer that?
I didn't see it.
Okay. The question was, what formats are the constraints? Can it take Xilinx XDC file?
So yes, it can, because there is a plugin to Vivado that I'll talk about in a little bit. I'm pretty sure I added that slide to this, that basically you go to the Vivado store and there's a Questa CDC plugin. And if you add that to Vivado and you hit that button, and it takes all of the constraints that you have in Vivado and it generates all of the constraints for Questa CDC out of Vivado and launches our Questa CDC. So it's not it's not exactly the same constraint format, but there's an automatic conversion from Vivado into the scripts needed to run ours. So hopefully that answers your question. Basically the benefits are you get this analysis up front at the RTL level. You're not trying to do this at gate level in circuitry where those errors are unpredictable of when they're going to occur. It's very accurate. It's going to find errors that other CDC solutions will miss, and it's not going to report things that are as errors that are actually okay. It's scalable in the sense you can do it at the block level on several blocks and then assemble that at the higher level. We can do hundreds and hundreds of thousands of gates, quote unquote, of RTL. But if it does get to the point where you have this giant design, you can do it at block level and then build it up hierarchically. It's very focused. So the workflow for this is you start with your RTL code. You can have your SDC constraints, your Synopsys design constraints. We do have formal libraries for all of the major vendors. So if you do have instantiated gates, or you have things like the DCMs, the PLLs, et cetera, from the vendors, you're going to want to bring those models in so that we can understand what the functionality of those is, and then do this analysis. So the synchronizer side of things, we have about 2 or 3 dozen different synchronizers that are built into the tool. So, 2D flip-flops, the simple ones, demucks, handshakes, FIFOs. And then if you need to, you can create your own custom synchronizers that will search for and detect, and et cetera. So the reporting, you'll see that you'll get violations. So these are definite errors. You'll get things that are green that says these are okay. And then you may, on that static analysis, get some that are called cautions. And those are, hey, it looks like this is okay. There's not an error structurally here, but we haven't been able to do a proof that you can't violate the timing. And then that is where you can now bring your test bench in and start to run data from your test bench and see if you can either promote some of those to saying, hey, we gathered enough data from your simulation to say these are now proven, or you'll get the opposite. You'll get a firing where we say, hey, based on your test bench, we see that this caution has now become an error. And I'll demonstrate all this as we go along. So as I said, an example here of how you would synchronize a bus is, normally you would be just holding the data that you currently have. And then when you have data you want to pass from one domain to another, you put it out here, you pass the control signal that says, go ahead and sample that. That gets sampled, this control signal goes away, and then we start capturing the current data again. So the protocol here is, you better put this data here, and this data better not change while this signal right here is active. And so if we can't find that, if we can't formally prove that you're not going to violate this, and sometimes we can, but if we can't, what will happen is we'll generate, and you can't read this here, it says assertions. We'll actually generate a set of assertions that goes into your simulation, that now you run your simulation, and it's going to verify for you that this data is never changing while this signal is active. And if it ever does, you'll get a warning that says, hey, I found a problem with your circuit based on that. So the protocol analysis is, again, you do that static step. It generates those formal assertions. You run your simulation, and then you get either proofs or firings that show a problem. The analysis part of it is, if you get those type of problems, we'll show you where that is. We'll flag those errors. I'm going to kind of go fast through this because I'm going to show you a little bit in the demo. And then as far as reconvergence goes, as I said, we do this reconvergence analysis where, so here's two examples of, I guess this is a single bit that's been properly synchronized, but then you'll see it goes through a flip-flop, then goes through some logic and comes to here. And so the reconvergence analysis will go ahead, it'll identify that this is a potential path, and then every place that it says, every time that it says, hey, these clocks are getting close enough that we might have a metastability issue, it will inject that metastability into your simulation. And what that means is it will control those two paths and say, on certain occasions, this path will have a 1 delay. Let's go back. On certain occasions, this path will have a 1. This will have a 2. On other occasions, they'll both be 1, both be 2, 1, 2, and it'll do that enough to the point that it says, okay, I've gathered enough data. So as I said, there is this new Vivado plugin. And so to use the Vivado plugin, you need to get, I'm not sure which version of Vivado. I think it came in whichever version came out about 6 months ago is when this was added. And so you go to the Vivado App Store and you grab the Questa CDC plugin from the Vivado App Store. You add that to your Vivado, and then you need to use Questa CDC 1.5D or later. And so basically what that means is then when you're in Vivado, you have your project, you've set up all your constraints, you can just go click that Vivado button, and then that'll launch Questa CDC and generate all the data you need to run your analysis.
Hey, Walter, there's a question from the audience.
Sure.
Can you look at the chat? It's a little long.
Okay. Let's see here. Chat. Does Autocheck and Questa CDC both use the same QuestaSim parsing engine, so our code compiles with Questa Autocheck? Yep. So it's basically the same front end that you've used to compile Questa, as long as you have a matching version, meaning if you're in 10.6 and that could be ABC, whatever. So a 10.6x and a Questa CDC 10.6x or an Autocheck 10.6x, then you don't even need to recompile. And so I was working with a customer, and he was trying to set up CDC, and he had a really confusing compile script, and he was trying to port it over, and he couldn't get it to work. So I said, all we need to do is take your existing libraries and point to them. And so we didn't even have to run a compile. We just used his compile script that he used to run his simulations, and we just pointed Questa CDC at his already compiled libraries. So does Autocheck and Questa CDC include the Questa Formal engine, or do we have to buy the formal tool separately? So Autocheck and Questa CDC are both part of our formal tools. So no, Autocheck, if you buy it, you have the formal engine. CDC, if you buy it, it's using the formal engine. So yeah, it's included. So if I just go to my last slide here is my summary, and then I'll go to my demo. Whoop. My last slide is for CDC is we are really the industry leading CDC tool, clock domain tool. We're complete, we're accurate. We are the only one that is currently certified by the automotive industry, which says something to you about all the other solutions that they are deemed not complete enough. So let me pop over here to my Linux screen. Kung, does this look good? I'm going to assume that everything looks good here. So I've got a couple of different demos I'll run. First, let me just run the static check for CDC. And so if you look at it, we have a make file here. And the make file is really just, you know, run vlib and vlog on my test bench. So it's exactly what you do for compiling code for simulation. And then CDC is I just go ahead and run that code, and then I'll show you the results. So not actually, didn't really need to look at that. So let me say make run, and I'm going to do this on a Verilog version of the design. So this is a fairly small design, but you see it ran super fast. On a 100,000 gate design, this would take maybe 10 minutes to run. So the first thing we'll do is let me show you those directives. So I've set up a few clock directives here. So I've got a CPU in clock that's 50 megahertz, a core clock that's 50 nanoseconds, 60 nanoseconds, and a Mac in clock that is 50 nanoseconds. These are all asynchronous clocks. If I wanted to define something as synchronous, what I could do is I could edit that and I could put in a clock group. And if I name two different clocks and I give them the same clock group, even if they're different frequencies, it says they're synchronous to each other. So I could say this 100 megahertz clock and this 50 megahertz clock are synchronous to each other. So they're in the same clock group. That means it won't do asynchronous testing on them. So, so for these, they are three different clocks that are all asynchronous. I put right here, I tied scan mode off to be a 0. So that was just, tying a constant. And then I put a few things just to make the tool run faster. My reconvergence depth, I only did as 1. Something on the handshake there. So now if I look at my clocks, so the first thing it does a clock analysis. So the good thing is here, I specified those 3 clocks, and you'll see it found those 3 clocks. And those are the 3 that I specified. I've specified their frequency, and it didn't find any other clocks. So that's what I wanted to see. Now, I didn't define any resets here, but if you look, it said, okay, I didn't specify any resets, but it did find two resets. One of them, this one is the input clear, is an asynchronous reset, and it goes to like eight registers somewhere. It also found this other primary input port reset, and if you look at that, you'll see that goes to a bunch of resets here, and they're asynchronous. And then it goes to a couple of different FIFOs, and in that case, it's acting as a synchronous reset. So if that, is good, okay, there are, as far as I know, there are only two resets. So that looks pretty good to me. So now I can go and I can look at what were the results that I got. So you'll see, if I look at my results window, let me just maximize this. I got 6 violations. So this first one is it's saying, okay, this signal doesn't have a proper synchronizer. There's no synchronizer that I found. So let me look at that. And I see, oh yeah, here's a register in the green domain. It's going through some expression. And even worse, what I'm seeing is I've got a signal that's from this purple domain. It's going into some logic from that green domain. And so this logic is highlighted as red because it's saying, hey, I'm mixing domains here. That's coming in. I am going to have problems here. So that's definitely a problem. I got to go fix that. Let's look at something from this one. It's saying there's combinational logic before my synchronizer. So let me look at that. And I see I do have a synchronizer here. I'm coming from the green domain, going to the blue domain. But what I'm actually seeing is that I'm getting data from 2 different registers in the green domain that are going through logic and coming over here. That's really an error because what we want to see is we want to see the direct Q output from our green domain going to the input of my blue domain synchronizer. So right here is some other errors, and it's basically going to be, a similar thing where I've got logic and I've got different flip-flops because you see these are red. So I'm coming from a couple of domains and I'm going across. So these are obviously just structural issues. I need to fix all those. Let me come down here and look at some of my provens. So here, I've got a purple domain register, single bit, going to some flip-flops. Perfect, no problem. The timing that I've specified from my clocks here, if I looked at them, this clock is obviously faster than this one because it's saying there's no issues. So here's a couple of provens. If I looked at all of those, they'd look like that. So those are proven. Now these are evaluations. So the difference between an evaluation and a proven is that this guy especially, let's look at it. So this looks good, but then if I look at this and I say, show me the declaration of that, you'll see that's actually a 4-bit vector. And I've just got a 2D flip-flop. And remember I said, I can't do that because there could be garbage because these are flip-flops. But what it's telling me is that it's figured out that this data coming into here is gray-coded. So only one of these bits is going to change on any one clock cycle. So it's saying this is okay because I've done the analysis that says this is gray-coded. So another CDC tool would flag this as a warning because it would say you're taking a bus and you've got 2D flip-flops. But because our tool is doing that formal analysis, it figured out that's gray-coded and said that it's okay. So similar things for this FIFO. And I don't know what was the issue with this one, single bit synchronization. Probably, I'm guessing the reason this is an evaluation is I bet if I track back, this clock is going to be, I would guess that's okay, that's the scan clock. This is the CPU in clock, which is 60 nanosecond period, and the other one, so my guess is that this clock is slower than this one, but it did the analysis and said this data rate is never going to change too fast. So let's look at this last set here, and this is one of these 2D flip-flops. So what I see here is here's a bus, and then there's an enable signal coming in that's just saying, so effectively this is that mux feedback. And what it's saying is that this data is here, this is structurally okay, but what it wasn't able to prove with the formal analysis was whether or not this signal could change while this signal is active. And so this particular demux, I'm going to have to go and do that protocol analysis. So that's where I would come over to here. And let me just make one. So this is going to do that same static analysis that we did before. So if I make file, whoops. If I look at this, the static analysis, so let me make debug. So this should look exactly the same as the previous one. This is, I don't know why I didn't just do it here. This is the static analysis step. So I should see those same two cautions on the demux and et cetera. So now what I'm going to do is I'm going to simulate this with the checkers that were generated from that static analysis. Make simulate. So this is just using my test bench, but it's going to include the assertions that I did before. So now I've run the simulation. So I'm going to say make debug sim. So now, oops. You'll see I have the CDC checks, which are the same as before, but now I also have this simulation tab. And you'll see I evaluated some things, and then I got a firing. And if I look at that firing, let me actually first look at the schematic. Show. Should be able to. Well, let's just look at the simulation firings. So let's look at this simulation firing. And what we'll see is it's flagging right here that I have a problem. And if I look at the signals here, we'll see this is that TX mask and that demux. So this is the data that I'm passing in. This is the data that's being sampled, and then this is the that enable signal after I've put it through the synchronizer. And we'll see that this data is changing while that signal is high. So it's flagging that as an error and showing me that it's a firing. So that's kind of how you can find these CDC errors quite effectively and easily. And I think we're at the top of the hour here, so I'm gonna skip the Autocheck demo. I can just do a quick make run and just kind of show you that it's the same kind of thing. I do the simulation, it runs the analysis, and then it opens the database, and I get a similar kind of thing where I have some cautions. So it's cautions on like unreachable blocks and unused ports and incomplete sensitivity lists. So if I look at that, I'll see I have this process that only has the C state, but it's using other signals. So that's an incomplete sensitivity list. I have warnings for like, or errors for like combinational loops and deadlocked and undriven logic. But I'm gonna kind of stop the video at that because we are at the top of the hour. But I will see if there's been any more questions. No more questions in the chat window. You're welcome to put any more questions there, or if you can unmute your line and ask them live, and just see if there's any more questions that come in. We'll give that a minute or so. And if they're not, I will say thank you guys very much for your time and attention. If you have any questions, contact EA Direct. Kong, I don't know if you had put your contact information in the chat window. You can put mine there as well.
Put the information for if anyone would like, you know, the copy of the presentation and the link to the video recording. Please contact Jenna. I put that in the chat window. So let us know, and we would love to chat with you to understand your particular needs. Questa is a platform with many other options. We are just talking about the Autocheck and CDC today, but there are other things, you know, system Verilog, UVM, and all that feature. So we would like to talk to you to understand and to recommend the proper solution. So at this point, anybody has questions, please unmute yourself. We can answer live here. Okay. And if not, thank you for attending today's webinar, and thank you, Walter. Appreciate it.
Thanks, everybody. Goodbye.
Bye.
Thank you.